that we have to go 5-minute overtime again. And my Italian friend here is my witness. I really appreciate you came today. If we had won, I wouldn't be here. I still can't believe it. Okay. One more to go. So, we looked at models for the large-scale and small-scale turbulence regime by Dammköhler, and these really capture all the physics. And so, but they are, two different expressions for two different regimes. Turns out one can derive an expression for the turbulent burning velocities that has these same limits, that goes to these expressions in the right limits. And one can derive that from an equation here for the flame surface area ratio. Flame surface area ratio, that was this sigma we had introduced earlier. And this is very nice. So one derives an equation for that sigma. Let's see, you can see that equation. Let's say here, that would be an instantaneous equation for that sigma. And then what we see in this equation, there are some production terms. Well, there's of course the production term, it comes from turbulence. And there are two different dissipation terms. One is a dissipation term that takes out flame surface just by burning. We call this the kinematic restoration. And again, the simple physics behind this, you have something like this, had a lot of flame surface. But if you see this burns this way, this burns that way, and so once this is burned out, you have taken out flame surface. Just the process of burning itself eliminates the flame surface. Now, that's what's called kinematic restoration, and then also there is a dissipation of flame surface just by, again, the curvature effect. And you can look at it like this also. If there's very strong curvature here, and just by a diffusive process, the flame surface goes away. So that is the that would be that sigma equation. And now the assumption is that these terms are being modeled. Let's see if we have the mean equation here. This is the mean equation, and now you have all these terms on the right-hand side. And then we say, we introduce models for these, and then we assume that production equals dissipation in that, so that the production of flame surface is equal to the dissipation of flame surface, which then we can discard here these transport terms on the left-hand side, and then this can be solved for the sigma turbulent, and then that gives you an expression for the laminar burning velocity. So this leads to then an algebraic equation like this, and at the end of the day, this is what you get. You see there are lots of coefficients. These coefficients mostly come from theory. You see that here delta S, that would be S turbulent minus SL, so that's the increase of the burning velocity by the turbulence. And that now is a function here of L over LF and V prime over Z. It's a quadratic equation because this was a quadratic equation, so quadratic solution, and so on. So, there's a table with all these values here, and most of them come from either here, let's say, definition, or from some theory, or here typically used values like this. And then here there's this coefficient here. That's actually the proportionality coefficient here in this relation. Dammköhler set that equal to 1. That was also found from DNS and so on. So, anyways, once you have all of this, then we can plot this here again. And that line I showed you earlier, that actually comes from this. Now, what's interesting is, let's see. So, first thing is you can write this also as a function of Dammköhler number. So if you, instead of write St over SL, you write St over V prime, then that is a function only of the Dammköhler number. Okay, and then if you go look at this equation to the Dunkel number, then you can look at the limits for small Dunkel number and for large Dunkel number. And then what you see is that doing this, let's use that shown here. So. It's not shown here, but if you do this, you can try it out at home. If you look at the limits, large or small Dunkel number, you will find exactly these limits back again. You know, the limit that small Dunkel number, then here this is 0, and it becomes small, and you will find that ST is proportional to V prime, and in the large Dunkel number limit, you will actually find you know, this relationship. Okay, so this has both of these Dunkel's limits in the large and small limit. And now one can look at comparing this with experiments. Again, so these are. So this here is ST over V prime, essentially as function of Dunkel number. And what's interesting is. Yeah, you see, so this, the black line, that's the model here. Then you have all these points. These are all individual data points. And you see, you know, there's a huge spread here. But then you can take the average of this. If you take the average, you know, conditional on the Dunkel number, you get these black points. You see the black points actually, they correspond quite well to the model. The other thing you see here is that, just from the data now, is that ST over V prime, that goes to a constant for large Dunkel number. Right? That's equal to 2 for large Dunkel number. Which means, which just shows that you know, Dunkel's large-scale limit is included here, because that basically means ST is proportional to V prime, and the proportionality constant is equal to 2. Okay, that's so that's what the model includes here, and then this here would be Dunkel's small-scale limit, and then here you see there's a very, very strong dependence here on the Dunkel number. Okay?
So,
yeah.
Does that kind of mean that as we go to higher and higher number, somehow the turbulence becomes more important? Because it seems like you're saying velocity fluctuations are going to control the turbulence velocity.
Yeah.
And chemistry kind of is.
Well, what does large Dunkel number mean? It basically means that the chemical time scale goes to 0. It gets very, very fast, and that means the flame becomes thin, and that then means that you know, the turbulence doesn't see the flame structure anymore, and then it's basically just the you know, the turbulence that generates flame surface, and that flame surface, and we had the discussion in the break, in turbulence theory is always the production process that's most important, because we always assume the dissipation comes anyways. As long as you create a fluctuation, that flame fluctuation that will dissipate it. And so here's the same thing. As long as you create flame surface, it will be taken out by these dissipation processes, curvature, and the you know, the burning itself. So it's called kinematic restoration. Okay. Other questions about this? Okay, so that leaves us some time then to briefly talk a little bit about non-premixed combustion. And if we get through this in time, then at the end I want to show you, you know, one example, short example of simulation, large eddy simulations actually, of a complex kind of geometry. and predicting emissions from this. Okay, so first thing we want to do here is we want to look at, so we talked a lot about non-premixed combustion already. We derived these flamelet equations, and same thing as what we talked about here. We said these flamelet equations, they tell you, all the mass fraction is a function of mixture fraction. Which means if in the flow you know what the mixture fraction distribution is, you can map the temperature into that field. And that's kind of what we do. And there's one little trick missing, and we'll talk about that. But maybe first, we want to talk about go back to remember for the laminar flame, we looked at an analytic solution, a similarity solution that ultimately gave us the flame length. And here, we want to do the same thing for the turbulent flame. Now, this is how it looks like. You have you have an inflow here, and then you have a stoichiometric contour. There's rich, there's lean, somewhere in between it must be stoichiometric. And then we said, where the stoichiometric surface hits the center line, that's where we want to say that's the flame length. Okay, and then you have these equations here that describe, now we talk about the Reynolds equation, the mean equations that describe the problem. And you see here there's a turbulent diffusivity, and we have these three equations basically: velocity, momentum, velocity, the continuity equation, and then the mixture fraction equation. Now, nu t, the original equation. So what's interesting now is that the original equation look very much like this, with the exception that this here now has the nu t. That's basically the only difference we have. And the nu t, there's a model for this. Nu t here is equal to simple model u times d divided by 7. Okay. So that model was, found to, predict some results. And what's interesting now is that because the equations are essentially exactly the same, just that one, part has a different meaning, we can develop the solution in exactly the same way as for the laminar flame, just keeping in mind that this nu and the nu t are a little different. And so this here was the similarity coordinate we had, and now, the similarity coordinate here is essentially the same except for introducing the mean, and the same here for this transport parameter, except that this now is a turbulent transport, and this was a molecular transport. But otherwise, it's the same thing. And then, you can develop the solution in exactly the same way, and this is what you get. And the most important thing here is that the spreading rate parameter here now is a little different than what we had for the laminar case. This here is kind of a turbulence Reynolds number, and this is a laminar Reynolds number. However, what we see is, what we found here is that the centerline velocity, it goes with 1 over the distance from the nozzle. And that's the same in the laminar and the turbulent case. And for the mixture fraction profile, it's the same thing. It also goes with 1 over the distance from the nozzle. And we have the same thing in the laminar and the turbulent case. Okay, so finally, we can take the solution here for mixture fraction and set it equal to stoichiometric, and then evaluate what the x is at which this would happen. And this gives us the flame length. And then this kind of looks like this. That, again, this looks very similar to what we had earlier, except, again, that now this here is a turbulent transport coefficient and not a laminar one. Now, what's interesting, you take very old experiments that suggested that that the flame length scales like this, with 1 over z stoichiometric, and then the density ratio. And you see, we find the same thing kind of here also. And see, we have this C parameter, and if we want this and this to be the same, we just have to use the C parameter here like this. Okay, and then we get these two different solutions. And now one thing that is and that's the main difference. We said earlier, if you have the cigarette lighter and you crank up the flow speed, then the flame length became larger. Turns out for a turbulent flame, you crank up the flame speed, speed, it doesn't become larger. Because we said this here, that should be equal to 70. That was our model. And so you see in this case here, this Reynolds number is a constant. And in this case here, it's not a constant. Okay? So that's the big difference between the laminar and the turbulent jet. And if you compare that then with experiments, this is kind of how the experimental value looks like. And you see, this here would be the linear increase. You see that for very small Reynolds number. And then for very large Reynolds number, you see that this is constant. Okay, why is that? Why does it not change anymore? Well, think about it for a second. Yes? Question is, why does it, in a turbulent flame, I increase the flow velocity? Why does the flame so we found the flame length does not increase. Okay, and the question is why? Can anyone physically explain this?
In a laminar flame, it needs more distance in which to burn out, so it gets taller. But in a turbulent flame, the mixing is increased, so it reacts.
Right. So exactly right. So in the turbulent flame, you increase the velocity, which means actually the flame now wants to be longer. But increasing the velocity also means you increase the turbulence. And if you increase the turbulence, then you get more mixing, and this just cancels out exactly. Okay? And interesting fact, I think. Okay, good. So but that's just on the sides a little bit. Question here is how do we model turbulent combustion? And we said earlier, well, we have these flamelet equations. In one model that is very simple and very powerful also, you can't use for everything, but it is still a very powerful model, is to take the flamelet equations and assume that these flamelet equations are in steady state. Okay? It's called the steady laminar flamelet model. If you do that, then you can solve the flamelet equations as function of mixture fraction and the dissipation rate. And you can compute all species mass fractions and the temperature as function of Z and the dissipation rate. Okay? And so that's a so-called flamelet library. This means now, essentially, you have to know in a computation, you have computational cells, and if in that one computational cell, you know what the dissipation rate is, and you know what the mixture fraction is, you can go in your library and look up what the mass fractions are. Okay? So that's simple. That's what we call a conserved scalar-based model. Conserved scalar-based model basically means you solve the mixture fraction, and you know the mixture fraction, and then the mixture fraction is a conserved scalar, and then you have some sort of chemistry solution as function of that conserved scalar. Okay? Are there other conserved scalar-based models? Anyone knows another conserved scalar-based model? Yeah, there's another model. It's called the conditional moment closure model, where you solve equations that are very similar. Actually, the first order is the same as the flamelet equation, but simpler. I mean simpler model. Anyone knows simpler model? We talked about the. Say again. Oh, G equation is not simple. That's complicated. No, the G equation, we use that for premixed combustion. Here we're talking about non-premixed. But of course, you know, in the real world, usually, not usually, but very often you have some mix of premixed and non-premixed. And so we combine these two different models together. We do that. But so there's a formulation for partially premixed combustion. But no, I'm just here thinking simple.
We talked about the whole combination of temperature and heat outside of the species earlier on.
Yeah. So we had something where we assumed infinitely fast chemistry. And from that, then, we computed what the mass fractions are as a function of mixture fraction. We did this in the, I think, first lecture, first day. And that's the so-called Berke-Schumann solution. Okay? And so Berke-Schumann solution, infinitely fast chemistry. You could just, again, if you know in one cell, you know your mixture fraction, distribution, whatever, then you could also use that. Okay? But that is infinitely fast chemistry. Or you could use chemical equilibrium. Okay, that also would give you something. Although that's not all that good. But anyway, so now for these conserved scalar-based methods, as we said, you need to know the mixture fraction. And now let's say you have a laminar case. Let's say you compute some laminar flame, laminar jet flame. Let's say it looks like this, and then you have a computational mesh. Like this, and then in each computational mesh you have one value of mixture fraction, one value of dissipation rate, and you can do exactly what I just said. You go look in your library and you find the, all the mass fractions and the density, and now you know the density in each cell. Okay. Now problem, not problem, but a little more complicated, is that in a turbulent flow, if you compute a turbulent flame. Think of rands. Okay, this is my flame, and this is another instant, and then here's yet another instant. Okay, different times this flame will look differently. And if I have a cell here like this, then in this cell I don't have one value of the mixture fraction. I have a distribution. Okay, and so here I have a PDF, there's an expectation to find certain values of the mixture fraction in that cell. Okay? So, in a turbulent flame now, I need to know what the distribution is, the PDF of mixture fraction in each cell. And so, in order to do this, it's good to know what the mean is. It's good to know what the variance is. And so the first thing we do here is we derive equations for the mean and the variance. Here's the mean. We've done this earlier here with the scalar flux model. Okay, and this is the variance equation. And we talked about this variance equation also before. What you see here is, again, I'm running back and forth because I want to see this equation also. Okay, so here we have, again, this is scalar flux term. We will model this here like a diffusion term with a turbulent diffusivity, and then here there's a production term where we already used this model, which was introduced earlier already for the mean equation, and then here we have the dissipation term. Okay, and for the dissipation we also had a model. Let's see, it's here, the dissipation. That came from the assumption that the timescales, the scalar timescale, the scalar turbulent timescale, and the mechanical turbulent timescale, or the turbulent timescale of the flow, that these are the same. And so a timescale here for the flow is given by epsilon over k, the timescale of the turbulence. The timescale, or let's say k over epsilon would be the timescale, and the timescale of the scalar would be chi divided by the variance of mixture fraction. And so we assume these are the same or they're proportional, and this is the model. You plug this in here and you see the equations close. Okay? So with these two equations now, you know the mean and the variance. This coefficient here is discussed here. There's people use different values for this. This is a coefficient, same coefficient also appears in the closure for the PDF transport equation model, which we discussed earlier. And people use values all the way from 1 to 10 or whatever. And 2 is a very typical value that's used for this. But the only thing we know, not the only thing, but one thing we know about this is not a constant. It varies in the terminal fields. Okay, let's skip over this. All this says is that if the flow is adiabatic, say you have no heat losses, like take a jet like this. You know, there's no wall and heat transfer or whatever. And let's say there's no radiation. Okay, or radiation can be neglected. Then what you see is an equation that describes the enthalpy has mathematical similar form as the equation that describes mixture fraction. They are the same. They both have a convection term, a turbulent transport term, and that's it. They're both conserved. Enthalpy is also conserved. Okay? If there's no pressure change. And if that's the case, then you know, these also have the same boundary conditions, right? I mean, you have a jet like this. You have one mixture fraction in the fuel and one in the air. And similarly, you have one enthalpy in the fuel and one enthalpy in the air. So they're mathematically similar, and they're just linearly related. However, if you have, so you don't need to solve an extra energy equation if you have mixture fraction equation. However, if they have different boundary conditions or different, you know, source terms, you know, you have evaporation, or you have, or the pressure term dPdt is non-zero, like in an engine, then you need to consider an energy equivalence. And this is for how it works, if you need it. Okay. Now we need the PDF of mixture fraction, and we have the mean and the variance. Now, typically, what people do is they presume a certain shape of the PDF. Okay, and you could imagine if you have the mean and the variance of a random variable, then you know typically what people do is they assume what? Gaussian. Okay, Gaussian always sounds good because why? The central limit theory tells you everything has to be Gaussian at some point. You know, as long as things are complicated enough, they should be Gaussian, and we think this is complicated. Okay. Now here's the problem: Gaussian gives you non-zero probability for values of -50. Okay, the mixture fraction is positive. Okay, so people have used the Gaussian, and then they use the clipped Gaussian. Okay, so you clip it at 0, you clip it at 1. Mixture fraction is defined only between 0 and 1. Some people have used clipped Gaussian, but then you get it's still funny behavior at 0 and 1. And then people came up with another thing. It's called the beta function. And all the beta function is if the, so this is the definition. Let's just go through the definition real quick. Beta function is defined here like this, a function of z then. And you see it has these two parameters, alpha and beta. And it depends on the gamma function. And the gamma function is just a mathematical function. And you find libraries for computing this. But the alpha here and the beta, they are related to the mean mixture fraction and its variance. Okay? Now, this is how it looks like. Turns out that for very, very small variance, let's say you have a mean of 0.5 and the variance goes to 0, then this actually is the same as a Gaussian. It becomes Gaussian. So if the distribution is far removed from the boundaries 0 and 1, then this distribution becomes Gaussian. Another problem that you have in non-premixed combustion is this. And that wouldn't be captured with a that would be captured with a Gaussian. Is this? Look at what happens very close to the nozzle. Okay? Very close to the nozzle, I do an experiment here. There's not been much mixing, but the turbulent jet goes like this. So I do measurements, and all I find is either I'm in pure fuel or I'm in pure air. Okay? Because there hasn't been much mixing. What kind of a PDF does that give me? Gives me a double delta function, right? There is the delta function at 0 and the delta function at 1. And depending on, you know, how much contribution I get from each, you know, they have different strength. But interestingly, this beta function, for large variance, it goes to a double delta function. Okay? And you see this here. Let's see, let's go back here. Gamma is this divided by variance. So large variance means small gamma. And so if I have a big gamma, then you see I get something that looks like a Gaussian, but it goes to 0 here, you know, at pure. So Z equal to 0, to remind you, is pure air. And this would be pure fuel stream. And it goes to 0 at these points. But then when the variance becomes larger, which means here this gamma value becomes smaller, then you see it gets broader, and at some point it flips over and gives you a delta function. Okay? So that has the beta function has these nice properties. It goes to a Gaussian for small variance, which is what we would expect, and it goes to a double delta function for large variance, which is also what we would expect. And in between it, there's something. A lot of people have looked at, you know, compared this function with experimental data. It turns out, you know, for most part, it's quite good. So, so that means we actually have a model now for the PDF of mixture fraction, and that's good because, you know, if you have a model for the PDF, then and the model for the PDF just depends on the mean and the variance. So we solve equation for the mean and the variance. From that, in each cell, we can determine this PDF of Z. We have species mass fractions and temperature. We have these as function of Z, you know, from the flamelet library. And so you can actually integrate this to give you the mean. Okay? So this integration gives you the mean in each set. Okay, so what people typically do is, rather than doing this integration, rather than solving equation for mean and variance, determining these in a cell, then computing with all the gamma functions, the beta PDF, and doing this integration, you can actually do this integration beforehand because the beta function has only two parameters, the mean and the variance. Okay? Let's say you compute this for all possible combination of mean and variance, kind of a two-dimensional space. Then you can do the integration beforehand. Okay? And that gives you the mass fractions then, the mean mass fractions as function of mean of mixture fraction, variance of mixture fraction, and the dissipation test. Okay? And then you can store that as a flamelet library. That's what people really call a flamelet library. And then in an actual simulation, you just determine, you solve equations for mean and variance. And from that, you can also compute the dissipation rate. And then you just go to the library and pick your mean values immediately. Okay? Okay, turns out here for the density, because the density you use is not a Favre average density, it is a Reynolds average density because of the Favre averaging. That's just how it comes in. You've got to be a little careful. You actually integrate over 1 over the density and so on. But that's a detail. Okay, and then here this is mentioned again. With this, once you have the PDF of the conserved scalar, you can use any conserved scalar-based model, which would be a flamelet model, or a Berke-Schumann solution, or here, let's say, you could use reversible infinitely fast chemistry, which is chemical evolution. Okay, so now we could look at, does that make any sense? Is the Burke-Schumann, isn't that as good as the flamelet model and so on? And so for that, we can look at data here for turbulent flames. This here is old data here by Masri and Barlow, and in the turbulent jet. And if you take the data at a certain cross-section, you can plot the data, all these mass fractions here, or mole fractions. You can plot these for a given cross-section. You can plot these as function of the mixture fraction. Okay? If you measure the mixture fraction and the species at the same time, you can plot one as function of the other. That is an interesting thing to do, no matter if you want to do modeling or not. If you have that data, plotting it like this will tell you something about what's going on. Remember what this tells you if you look at a plot like this? Can you tell me where the heat releases? Where the H2 goes to 0, that's right. But I want to, I mean, you see this already, but I want to go back to, remember we had these flammable equations and we said the curvature of these profiles is equal to the source term, okay, times that coefficient and so on. But the curvature of the profiles is proportional to the chemical source term. So you see, for each one of these, you see where the chemistry happens. You see here temperature, heat release. It happens only in this very small region. All of this is just mixing. Okay, no curvature. You see hydrogen here goes to 0, and there's no curvature here. But then right here, there must be curvature. I don't see this because of all the data points. But when it goes to 0, that's where the chemistry happens. And same here for the for oxygen and here for H2. Okay, so just looking at this curvature tells you where the chemistry happens and where things are chemically inert. Now, so what you see here is these lines represent chemical equilibrium. Hydrogen here is the fuel. So what you see is chemical equilibrium is actually not bad. Okay, it represents the you know, these values here quite well, let's say. Okay, so this is the chemical equilibrium line, is this here. And then these here are different flamelet solutions, let's say, with different dissipation rates. They're here written as counterflow diffusion flames with different strain rates, but these are equivalent. Okay, and then you see that, you know, there are changes here. The temperature changes with strain rate. But you see here in this, which explains why you get so much variation here in the temperature profile. So look at this, the equilibrium, that's kind of the highest temperature here. And in reality, you don't have equilibrium, you have residence time effects, and this gives you then lower temperature. And that's what you see here also. Now, we look at other species, like OH, you see equilibrium is really bad. This is equilibrium, and this is the OH, mass fraction. And now if you look at how does OH look like in these you know, flamelet solutions, then you see this equilibrium, and this is and these two are here 100 and 1,000, and this here is 10,000. 10,000 goes down. So from equilibrium, which would be dissipation, so let's say this is proportional to dissipation rate, which would be dissipation rate of 0 to 100, 1,000, 10,000. What you see is the radicals, they start low, they go up, and then they drop off. They drop off when it comes to extinction. So this here must be very, very close to extinction. Okay? Now I compare this with this here, you know, 0.01, you know, somewhere between 0.05 and 0.015. Then you see, it's kind of what you get here. So including this effect of strain or dissipation rate would give you better results. Let's see. Interesting is, what happens if you do the same thing for, so here we said equilibrium. That was actually pretty good. What happens if you do the same thing for a methane flame? How would that look like? Temperature. Let's say this is how equilibrium looks like, roughly. No, I'm sorry. This is how Berke-Schumann looks like, okay? Full conversion, irreversible reaction, infinitely fast, okay? And then this is how the measurement roughly looks like. It's not exactly on the line. I just want to say, you know, it's especially here, actually, you will see a little difference, but it's not all that bad. What if you look at chemical equilibrium? What would happen? Who thinks it would be the same? No one. Good. Let's say this was the goals of Italy yesterday. Okay? Who thinks it's very different? One, 0 for Germany now. You were the goals of Germany now. I can't change it. Anyways, it is very different. What happens is, this is equilibrium. In the lean, it's almost exactly the same. In the rich, chemical equilibrium for methane forms, let's say, some method, and this method recombines to give you C2H6. So on the rich side, you have a lot of carbon, you have a lot of hydrogen, and in equilibrium, you get a lot of ethane, acetylene, C3 species, C4 species, and so on. You just form a lot of very big hydrocarbons. Okay? What does that mean for the temperature? It has to go down, right? Because this is stuff that didn't burn. So equilibrium here looks like this. Okay? So be very, very careful using equilibrium for anything else than hydrogen, except for the lean. Okay? The lean part, you don't form these species because you don't have excess carbon as on the lean side, as on the rich side. Okay? So be very careful with equilibrium. Okay, so we talked about the PDF, and here, I guess, you know, it's just a review of how these flammability equations are derived, but we did this earlier, so we don't need to go in any details of this. What is pointed out here, and maybe it's too much of a detail for what we're discussing, is that you have this parameter here, dissipation rate. And when I said earlier, we solve these equations as function of dissipation rate, or with dissipation rate as a parameter. So we use just all possible values of dissipation rate we can think of, and you know, and then we build these flammable libraries. And there's one thing here that one has to be mindful of, and that is, when I said dissipation rate is a parameter, actually dissipation rate here is a function of mixture fraction also. You see this? There's nothing that says this is one value. This is a function of. So what is this? This was the dissipation rate was proportional to the gradient of mixture fraction. Okay. In a non-premixed flame, let's take this counterflow diffusion flame. The gradient the mixture fraction between the two nozzles goes like this. Okay? So dissipation rate is 0 here, dissipation rate is 0 here because the gradient is 0, and it's maximum here. Okay, so it kind of looks like this. So it's a function of mixture fraction, and we need to model this function somehow. And so what we do typically, let's see if it's mentioned here. What we do typically is, maybe it's not mentioned here, you take a counterflow, and we saw that actually, we didn't go through the details, but we saw it very briefly. There's an analytic solution for what the dissipation rate is for a counterflow. And it turns out, what I draw here like what I draw here, which looks like an inverse complementary arrow function to you, maybe. Turns out that is an inverse complementary arrow. So that is the analytic solution. And so we use that analytic solution that we get from a simple configuration. We use that in this computation. And it turns out that inverse complementary arrow function that has just one free parameter, and that fixes the dissipation rate at one value. We typically fix it at stoichiometric, because stoichiometric, that's what's most important. Okay, so that's just a little detail here. And once you do that, you can solve it, and now you see it's the stoichiometric dissipation rate that appears here as a parameter. Okay, let's see. Oh, this is this function here, right? Dissipation rate is exponential and so on, inverse complementary error function. And so this is a little hard to evaluate this numerically in code. It's not so hard, but and also you could argue now, well, that relies on assumes that you have a counterflow, and it turns out if you don't assume a counterflow, if you assume just a mixing layer, you get the same solution. So this is a solution that you don't only get for the counterflow, you get it for other configurations also. And there are also simpler functions that describe this dependence. That one could use, but it turns out doesn't make a difference. What to use? Okay, so there are some details here on how you evaluate this parameter now in a turbulent flow simulation, and you can look this up if you ever need it. It's not very complicated, but I think we should skip this here. And then here we have now solutions to these flammability equations that you would get in case you don't have a steady state configuration. So I showed you what to do when we say, oh, these flammability equations are in steady state, and you can tabulate this and all of that. But how, if you're interested in engines, for internal combustion, diesel engine, for example, the diesel engine, you inject the fuel, and then you get ignition at some point. So that's of course not steady state at all, and you have very strong changes as function of time. And in that case, you can use unsteady solutions of the flammability equations, and that's shown here. You see here, this would be a state right after, let's say, compression, and this is the point where the fuel is injected, let's say. And what you see is the temperature here, is hot. Here the air temperature is hot, the fuel temperature is a little lower. But if you let this go for a little bit, then you see that the temperature here starts increasing slightly a little bit, and then it ignites here at this point, and then you see you kind of get a reaction front here that goes towards the lean and towards the rich. And what's interesting here, and maybe some of you guys know this, is that stoichiometric, we said, for typical fuel, this is probably N-heptane. For typical fuels, the stoichiometric is about 0.05. For heptane, it's 0.06. Okay, so let's see what happens at 0.06. That would be around here. And you see that's where the maximum temperature is, okay, once it's burning. That makes sense. Does it ignite also at stoichiometric? No, it ignites in the rich, in the very rich actually. You look at this here, this is about 4 times the mixture fraction of, or 4 times stoichiometric mixture fraction. And this is where it ignites. And does that make sense? Yes, it makes sense because if you just have fuel and oxygen, no radicals, and you have all these oxygen flying around, and they're looking for all these hydrogens and carbons. But the carbons, you know, they're all shielded by the hydrogens anyways. They're all, a lot of the fuel mass, actually, that doesn't participate in the early radical production process. And so that is why a very rich mixture actually ignites much better than a stoichiometric mixture. The other thing that's interesting here is that you see that because the fuel is typically colder than the air, there's a temperature increase if you go towards the air. Okay? And so you would actually expect that it wants to ignite over here because, you know, typically higher temperature gives you, you know, better, shorter ignition, and, you know, when you have this NTC behavior, which you might know, this might not be the case, but typically that's the case. But so you see you have competing effects here. The richer mixture wants to ignite earlier, which means ignition takes place over there, but then also the hotter mixture wants to ignite earlier, which means ignition wants to take place over there. So there are 2 competing effects, but you see here the richer mixture wins, and that is partially because it's right around the temperature roughly here where you have this NTC behavior, so the ignition delay time doesn't depend very much on the temperature. Okay, so I think this is all I want to say about modeling non-premixed combustion. And if we have some time left, we have a little time left. Maybe we can stop earlier today, which would probably also go well with Professor Law's plan. But I want to show you some applications, LES applications, very briefly, LES applications. Any questions about this?
About this one. You're saying that richer mixture wants to ignite where the abundant fuel. Does that say that the fuel breaks down at higher temperatures before ignition?
No. See, the higher temperature is actually on this side, right? But still it ignites over there at lower temperature. And that is because well, think in terms of equivalence ratio. Take the so you would think at stoichiometric everything should burn best, okay? Because, you know, each oxygen has a partner, you know, to do some work. But if you have a fuel, let's say like N-heptane, or what is this, and pentane, okay? And now I have stoichiometrically, I have a lot of oxygen here, right? And that oxygen, you know, it can try to react with this. But you see in the very early part, later on you have all these fragments, and, you know, the oxygen tries to do something with these fragments. In the very beginning, you see all these carbons here, they can't even participate here in the reactions. And so if you take these out, then you see overall, actually, it seems like this would be very fuel lean, because these guys, right now they're inert, they don't do anything. And so you have to have a lot more fuel to make up for this, you know, to provide more fuel. Yeah, right. Okay, other questions? No, okay. So there are 2 things I wanted to show you Yeah. Yeah, go ahead.
When you parameterize the mass fraction by seeing and chi stoichiometric.
Can you parameterize the fast
When
reaction?
you're characterizing, parameterizing yi in terms of chi stoichiometric, is that very accurate for turbulent flows? I mean, because the scalar distribution rate should vary with c, and we're using just one value at the stoichiometric.
Well, when you solve these, when you solve the flamelets, then you actually use the chi as a function of z. Okay, and it kind of assumes that locally you have these mixing layers, that you have stoichiometric, and then you have something leaner on one side, something richer on the other side. And then you get this kind of a bell-shaped distribution. For very, very high turbulence, it turns out that you should get something that is more flat than that. But typically, we don't have these very, very high Reynolds numbers in most applications. And so, if you have something like this, or at lower, this space where you have something like this, or like this, then it turns out you have this functional dependence, but you can parameterize these with just one value, okay? And it could be, you could specify the dissipation rate of, or some value here to characterize these profiles. Typically, what we do is we use the stoichiometric value, and that's very good because also it turns out that that value is most important. If you have the right value at stoichiometric conditions, then you pretty much get the right result. And the right dependence at that point, then you pretty much get the right result. It doesn't matter too much what value you specify far away from there. Okay? Do you have a question?
In the last diagram, how does that auto ignition change pressure?
With pressure? Yeah, it gets turns out actually so this is how this looks like. How ignition as function of 1 over temperature kind of looks like this, right? For these longer hydrocarbons, and so if you go to high pressure, then it turns out that ignition delay at low temperature doesn't change very much. But then at higher temperature, it does change. So this is this would be the pressure dependence of ignition delay time. And so you see, it just becomes much shorter. And similarly also for the, now if you look at, how does the equivalence ratio dependence here and there look like, they look roughly the same. And you get here for these very, very low temperatures also, makes a difference if you compare lean with stoichiometric or stoichiometric with rich. There's a different dependence there also. But this is roughly how it looks like. That's what I said earlier. If you had very low temperatures and you increase the temperature, the ignition delay time becomes shorter, exponentially shorter. This is a logarithmic scale, yeah? But then at some point, you get to a regime where the temperature, where the ignition delay time with temperature doesn't change very much, or even gets longer again, okay? And then when you go to very high temperature, it goes down again. Typical for a diesel engine would be this here, let's say is like 40 or 50 bar. And then this point here is about 1 millisecond, and it's about 1,000 Kelvin. Okay, so this is roughly what you get. Okay, other questions? Yes.
So you showed us for this specific saturation happening, the ignition actually happens faster for each mixture. That's all.
How it depends on the fuel? That is pretty, I mean, you have that pretty much for every fuel. I don't know a fuel that would ignite faster for lean conditions. And that's the same thing. I mean, this is because, you know, in the beginning, you know, a lot of the fuel it cannot participate in the reactions. So you have a lot more O2 than, you know, you have possibilities for O2 to react with. Okay? So the shorter the fuel becomes, the less that should be an issue. Okay? But typically, you have to go very, very rich with these to really find the minimum. What is the minimum ignition delay time as function of, at some point, it has to go up again. You're very rich and it needs to go up again. But you have to go very far in equivalence ratio to find the minimum. Okay? And, but here, this is, because the temperature you get higher this direction, you know, there's a competing effect. Okay? Other questions? Okay, so let's see. We have about I know what we have about. But I want to show you, I'll show you just one thing and then we stop. The other thing I wanted to show you is a DNS study that we have done, actually presented in the last combustion symposium, where we looked at DNS of spray combustion, and spray combustion we would think is non-premixed, and so we do a DNS and we evaluate all the terms and look at what's premixed, what's non-premixed. What we found it was mostly premixed actually. So that is something that I thought is a good thing also to keep in mind, that much of what I said here actually said, let's say it's premixed, let's say it's non-premixed. In premixed combustion we have different physics than in premixed combustion we have different physics than in non-premixed combustion. And it's very important for a model to capture these different physics. If you have a model that doesn't know if it's premixed or non-premixed, that model cannot capture the important differences. And that is important for, things like emissions and so on. So that's very important. However, on the other hand, it's important also to realize that just because I inject fuel into air, it doesn't mean that locally, combustion is premixed, is non-premixed. Okay? And that's what one should keep in mind. Modern devices like, let's say, direct injected gasoline engines, they're not fully premixed maybe anymore. They have local variations in equivalence ratio, and there's some non-premixedness to this also. And as I said, when we look at aircraft engines and we inject the liquid fuel, that doesn't mean it's non-premixed. It might be premixed also. Although I showed you, we talk about premixed and we talk about non-premixed, and I showed you models for premixed and models for non-premixed. This, of course, is a 5-day course, and I can't show you everything, but one shouldn't just take this model or that model. There are combinations of these models and formulations of these models for specific cases, but also combinations of these models that should automatically see what the combustion regime is. And then if you go to yet other devices like, let's say, HCCI engines, then you have auto ignition also, comes into play. That's yet a different combustion regime. And then if you go to, modern HCCI, there's the so-called spark-assisted compression ignition mode of combustion now, which means you have a spark. That spark forms a flame front. That flame front develops, and it increases the pressure and the temperature in the surroundings, and that ultimately leads to compression ignition. Okay, so there, what do you have? And let's say that is based on a direct injected engine, and there must be some premixed, and there must be some non-premixed, and there's some ignition also. Okay, so one has to keep in mind that these things are, when we talk about premixed and non-premixed, it really just means that a model has to know locally and instantaneously what combustion mode is happening, and it needs to consider that, but it doesn't mean that we can just say, oh, there's a big device here, and we assume that it's this, and it's just premixed, and then we use that. So, I want to show you one example here, which is, I won't give you too many details, but the idea here of showing you this example is, we're looking at, I said a few times, or maybe we said at the beginning, what's the question we want to answer by doing combustion theory and doing modeling and all of that? The answer, the question we want to answer typically is, we want to know what the heat release is so we can know the densities. But for doing that, it's not so complicated maybe. Maybe some very simple models, they do the trick already. So why do we look at these more complicated models based on detailed chemistry and all of that? Because for emissions, this is very important. And there's nothing more complicated in emissions, I think, than soot formation. And so predicting soot in real devices is a big challenge, and I'll show you why that is. And let me see if this... oh yeah, good. This will come in a second. And then I'll show you another thing that I mentioned a few times, is the intermittency that you get, and the importance of rare events that you very often get. So, soot modeling is very complicated because, so this is a sooty flame here, and we looked at these before. But what happens here in soot formation is that you have the fuel, and it burns, and you have pyrolysis maybe, and oxidation. So the fuel burns somehow, and while you burn the fuel, you form some aromatics, and these aromatics grow into larger aromatics, these macromolecules, and then sometimes these come together and form here these three-dimensional structures, and that's what we call soot particles. So soot particles are basically big lumps of carbon and hydrogen, more carbon than hydrogen, which grow into these complex shapes. And the reason why this is so complicated is because you need to, because every single particle looks different, okay? How do you describe this statistically? You have to decide on what parameters you want to describe. You need a statistical model to describe these particles. And when we talked about turbulence, we said we need a statistical model to describe the turbulence. Now you need a statistical model to describe the turbulence, and within this statistical model, you need another statistical model to describe the particles. So that's part of the reason why it's so complicated. You need to describe particle dynamics, heterogeneous chemistry between the gas phase and these solid particles. Radiation is often important, and here I mentioned high intermittency. These are processes which are another reason why it's complicated is that there are a lot of physical processes that happen with these particles, which one needs to consider. Here, for example, these particles, once they form, they can actually come together, and they form either they form larger particles or they form these aggregates. That depends on the morphology of the original particles themselves. Then they interact with the gas phase, here with acetylene, let's say, to form larger particles. And then also you have pHs from the gas phase that condenses here on the surface, which also forms larger particles. And then oxidation, of course, gets rid of these particles, converts these carbon particles back to CO2. And what's interesting is, and that's yet another reason why it's so complicated, in a diesel engine, for example, you first form a lot of soot, and then most of that soot is oxidized. Okay, so the typical value is you form soot, and then 95% of all the soot you form is oxidized. and only these 5% they leave the engine. Okay? Now imagine you make a very small error. So you have a difference of two large numbers. Let's say you make a small error in one of these numbers. Okay, that means immediately you have a huge error in your prediction. Okay, so that's and in the gas turbine it's very similar. You form tons of soot because I said this earlier. In a gas turbine, you want to burn rich, close to the nozzle. That makes it very stable. Okay, when you burn rich, you form tons of soot, and then later on you mix it out and you try to oxidize. This is a high-speed video that was taken at Air Force Research Lab in Dayton, Ohio. I got this here from Mel Rockmore, and this is a gas turbine. And what you see here, flow goes from, this violates the first law of fluid mechanics. You guys know the first law of fluid mechanics? Flow goes from left to right. So this violates that. The flow here goes from right to left. This is the injector. You have a swirl injector, swirling flow coming in, fuel injected into this, and then you get you get a recirculation. That recirculation actually, you recirculate now rich gases. You bring this back, and that creates a very stable flame. And so what you see, this is just a video. So what you see here, the very bright kind of stuff, that is soot. Okay. And now watch what happens with soot. You form some soot here, and then mostly it burns out before you leave the engine. Okay? And then once in a while, you form a lot of smoke, and somehow, like now, and then somehow this smoke is not being oxidized, and this huge cloud here leaves the engine. And then, look after this, no soot. No soot, and so on. Okay? See, this is what I mean with intermittency. So when you see an airplane flying, and there's soot, you don't see this very often these days, but there's soot coming out of the exhaust. That's not because continuously you have a flow of soot. That is because you sometimes form soot, and then you don't form soot for a long, long time, and then you form soot. Okay? And that just happens on a time scale for you that you just see the smoke coming out. So that's very important. And then again, if you want to predict this with a Reynolds average code, there's no chance, because how does Reynolds average code is just solved for the mean, and the mean is a very small soot concentration, a very small non-zero soot concentration, which comes from 0 for most of the time and then one big patch. That's very hard to model in the Reynolds average context.
In the experiment you showed, so a must have one for control issues. You must have made sure this flow time it's not varying because of constant.
Yeah, they must have done that. I would say. No, but this is not only something you see from this experiment. That's something you see from other experiments also, and also what we see from simulation. Yeah, this video actually I cut this out. I cut this out from a very long video, because otherwise you always have to wait for this one time. But this is a very long video, and this happens only twice. This is the worst. This is the worst one, and there's another one. It's not quite as strong, but for most of the time, there's no. Okay, so I mentioned this. See, this is the size distribution here of these soot particles. You see there are lots of small particles, and then somehow there's a dip here, and then you have lots of very broad distribution of large particles. Question is, this is how they look like. And let's say you just know the size of these soot particles. You don't know the shape. What is the size, diameter or whatever? Let's take the volume as the size. Okay? Let's say you only know the volume. Then you can tell me if you have a spherical particle which has essentially very little surface, Or you have an aggregate like this, or like this, which has same volume, but tons of surface, okay? Now, is that important or not? The oxidation rate, I said earlier, oxidation is very important. The oxidation rate, that depends on the surface area, okay? So that means an error in the surface area translates into an error in the oxidation rate. So, yes, it is important, that's the point. You know, the statistical models that one has to use, and I don't want to bore you with this, I just show you an application now. So we have developed models for all of this, and I mentioned this to some of you yesterday, which is why I remember to maybe show this to you. We have worked with Pratt & Whitney for a long time, and Pratt & Whitney and many other all other engine companies. They always come and say, "Hey, can you predict soot?" That's the thing they can't do with the codes they have. They don't even use commercial codes. They usually have their own codes. Almost all the engine companies have their own code, and but they can't predict soot. Okay, and so we said, of course we can predict soot. And so we did simulations, like this, which we looked at temperature profile here or whatever, and it looked all right. And so we put our soot models in the code, and it was bad. It was off by like 5 orders of magnitude. This was 2003 or whatever. So I had a student, I said, hey, we need to go back and start from scratch. So we worked on the chemistry for a long time. We worked on the statistical models for a long time. We worked on some of the sub-models here for oxidation and fragmentation of particles and so on. And all these things. So we went through the entire modeling process again, and we made a lot of changes, and then the model was finally done. So I had 2 students who worked on this over the past 10 years, and then we decided the model is good again. It was validated with a lot of stuff, and I don't have this here, but we validated also with just jet diffusion flames and bluff body stabilized diffusion flames and so on. So we did all the homework, okay, and then we said, okay, now let's put this back again in the same simulation, really, we did for 10 years ago, and then let's see what we get. Okay? So this is the engine, this is a Pratt & Whitney engine, and you have the compressor, you have the turbine, and this is the combustor, and this is just a sketch here, but this is an actual simulation. You see this liquid spray here. You see this is the primary region where it's relatively rich. Another thing I want to say here, somebody asked me yesterday about boundary conditions. And boundary condition is very hard to specify always. Very, very large modeling uncertainties come just because of boundary conditions. What's very nice about doing cases like this, you specify boundary conditions upstream here, and then the flow actually needs to go through these swirlers. And these swirlers, they impact the flow so much that it essentially forgets the boundary conditions upstream. So when we do complex simulations like this, we don't really have any problems with specifying boundary conditions. And then, so this is very rich here, so you burn, you produce a lot of soot here, and then there's part of the air goes around this and comes back through these secondary dilution holes here. These are a big secret in the industry, we can't show these. So you get dilution here, and this is essentially lean here. So this is a so-called RQL combustor. Stands for rich burn, quick quench, lean burn. And the idea behind it is you want to have a combustor that doesn't form NOx. Okay? And if you don't want to form NOx, you need to stay away from burning stoichiometric conditions, because stoichiometric conditions, high temperature, a lot of NOx. And so you could burn all lean, but that's not very stable, we said this earlier. So what you do here is you burn very rich here in this zone. Very rich means low temperature, okay? And then you do very, very fast mixing. They call this the quenching. And then this is all lean, okay? So you never have stoichiometric conditions. Now, that's the theory, but that's how it's supposed to work. So we use here a jet fuel surrogate. We can, because we use flamelet models, all the chemistry simulations, they are done beforehand. So we can use as complicated chemistry as we want. These flamelet solutions You know, one flamelet takes about, 5 seconds to compute, or 10, or let's say it's a minute if you have a very complicated mechanism. By the way, if you ever want to, you know, do simulations like this, I have a code, open source code, that's on my webpage, and if you send me a request, I'll send you a password, usually within a few hours, and then you can download it and play around with it, install it, play around. There's not much documentation, but many people all over the world use it, and you know, there's lots of examples, so it's relatively easy to figure out, you know, how it works. So this is on my Stanford, if anyone's interested. This is on my Stanford webpage. You know, under downloads, there is this thing, and if you say downloads, you have to put in your email address and who you are, and then, you know, I get a request, and then I'll send you password back. Okay, so anyways, that's what we do. We just use this code to do these flamelet simulations. And here we look at two different cases, a low fuel air ratio and a high fuel air ratio. And everything else is exactly the same. Okay, and these are the results now. This is Soot, volume fraction. This is the low fuel air ratio, high fuel air ratio. And what you see here is very similar, or it looks very similar at first sight. You have on the left, or in both, you actually see you form a lot of, as I said earlier, you form a lot of soot here in this primary region. You see actually the soot formation is pushed down a little bit, and that is because soot formation also is a very slow process, so it takes a little time to form soot. You need long residence time. You see here in this region, you kind of have a little longer residence time, which is why you form a lot of soot there. Here, actually, because it's so rich here, you actually also form a lot of soot here close to the burner. Now, this is the quench zone, and you see by injecting here this, or the air, the injected air that comes here around, actually this forms, this here forms a lean combustion region, and you see all the smoke here is basically burned away very quickly. Okay? But then once in a while, again, you see that here a little patch, or here a little patch leaves the engine, especially for the high impedance ratio. You see this very light green, you know, here leaving the engine once in a while. But you see how much smoke is formed, and compared to how little leaves the engine. Okay, so this is why this is very challenging. So this then shows the comparison of simulation and experiments. This is the smoke number. This is a normalized value here. It doesn't have any meaning. But if we compare that here with the experiment, then we see this time is not orders of magnitude off. It's actually not so bad. You see, this is still a factor of 2 different. But the trends here are captured quite well, and also the overall magnitude is not so bad. Okay, and this is interesting because it showed that you know, we worked a lot to do the fundamentals right, to do the theory right, not use empirical models and all of that. We did DNS of this thing to understand, you know, the interaction of soot with the turbulence and so on, and all of that. And once everything is in place, plug and play. There's no tuning or whatever, and you get a result that actually looks quite reasonable. That's really, I think, what I just want to show you here. If you do things right, then sometimes you get the right answer. That's very good. Okay, but what's interesting about this now also is, let's say we get roughly the right answer, then we can go back into the results and we can look at how was this soot formed. Because now in the simulations you have all that stuff. And what's interesting is that nucleation, that's a process of you know, forming the first particles from the gas phase. Condensation, that's a process of having pHs condensing on the surface. So both of these processes, they depend on having large-scale aromatics that kind of either come together or stick somehow on the particle. Surface growth, that is the mass growth by interaction with smaller hydrocarbon, unsaturated hydrocarbon species in the gas phase, like acetylene. So actually this is all acetylene-based, and this is the so-called HACA mechanism. You might have heard this, H abstraction, carbon addition. So basically you have the particle, you take out an H on the surface, which means you have a kind of a radical site now on the surface of the particle, and you attach an acetylene to it, and all of a sudden you have increased the mass by 2 carbon. Okay? You do this over and over again. This is how these particles grow. So we have this PAH-based growth of particles and the acetylene-based growth of particles. And what you see here, interestingly, is that it's all surface growth based. Almost no mass comes from this. You see this is scale 0.25, so you wouldn't even see this on the same scale as this, or you wouldn't see very much. Okay? Now, I get very excited about this, but why is this so exciting, or why is this so interesting? This is very interesting because when we go to laminar flames, we see that this usually happens in non-premixed flames. This usually happens in premixed flames. Okay? Now here we have a gas turbine engine where, again, we inject liquid fuel into air, and you would think this is non-premixed. Okay? But the soot growth mechanisms would tell you the opposite. Okay? You would think this is non-premixed, but as I said earlier, we did DNS and looked at, of something similar to this. We tried to look at premixed, non-premixed. We found actually, even in these aircraft engines, mostly is premixed. And then also here these, the way soot grows also tells us this. And now what's most interesting is that model, the way it's formulated, it actually picks that up. Okay? It picks it up, and it picks up the fact that this gas turbine, although we use the gas turbine always as a prototypical aircraft engine, as a prototypical example for non-premixed, it picks up that it is actually mostly premixed. Okay, that's interesting. Now we did other simulations. This is actually from other simulations. It's not the same simulation, but it's the same engine. Everything else same. These are older simulations. We predict NO, and here you see actually it's so rich here. You don't form much NO. And then, after this, after the secondary air, though, the mixing is not ideal. And so you do get regions which are still pretty hot, close to stoichiometric, and you still get some NOx formation, or a lot of NOx formation downstream of this. And this just shows, those of you in fluid mechanics, this mixing is still a really, really important problem. Just mixing, of one stream with the other. Good. So we compared this with experiments also. We'll just show you that. And then, I don't know why this didn't go forward. Yeah. Interesting here, we did 2 simulations, one with radiation, one without. And although the temperature profile doesn't depend on radiation at all, it's exactly the same temperature roughly. NO depends very strongly. So here we have 250 ppm emissions with radiation, but 1500 without. So the reason for that is that the radiation it doesn't lead to net heat loss. It just leads to redistribution of heat from the highest temperature to a little lower temperature. That gets rid of the high temperature peaks, and that gives you then a lot less.
So does this mean other mechanisms for the with radiation, without radiation? You were talking earlier about how the mechanism may less of a part.
Yes, but we're not that far down here. This is actually thermal NO. Yeah, this is all thermal. Okay, this year was, I showed this from a different talk, and so this year was probably the conclusion for that talk. This year is interesting, this amurator simulation here, right? And I showed this here at the end to impress people with these nice colors here. Okay, good. I mean, that concludes the lecture here. Let me see if any questions. Can we go for lunch? Is that the question? Okay, good. So thanks everyone for your interest. Thanks. I hope you guys will make good use of this in your future life.